Chapter 15 in the abstract algebra series is isomorphic groups and Cayley's theorem. Problem number 1 says, what are the elements in table form in the group of permutations isomorphic to Z2 under addition? And as you should recall, Z sub 2 is a set that contains the elements 0 and 1. And below, we have the table for Z2 under addition. Notice that 1 plus 1 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then finally 1 plus 1 is 0 because we are in Z2. And Cayley's theorem says that every group is isomorphic to a group of permutations. So what I decided to do here is I decided to let P sub 0 represent the first row in the table, and the first row of the table we have 0 and 1, and then I let P sub 1 represent the second row in the table, which is 1, 0. So P sub 0 is an element and P sub 1 is an element, and those elements are just permutations on Z2. Number 2. What are the elements in the group of permutations isomorphic to the Klein 4 group V4? Below I have the table for V4, and remember what makes V4 unique is that the identity element is listed on the main diagonal, which means that every element is its own inverse. For example, if you take A star A, then you get E, which is the identity. And that same thing holds for E star E, B star B, and C star E, and C star C, rather. So what would be P sub E? Well, again, for all of these, the top row is simply going to be the row headers, or the column headers, actually. And underneath, we're going to have the distribution for each row. For example, P sub E is just going to be the distribution as E works with all of the other elements in V4. In other words, E star E is E, and E star A is A, E star B is B, and E star C is C. So P sub E is going to give us not only the header columns, it's also going to give us the row underneath for E star X, where X is an element of V4. So P sub A is going to be the permutation for row A, because A star E is A star A is E, A star B is C, and A star C is B. So this would be P sub A. Same concept for P sub B. If you look at P sub B, again, we have the column headers here, and B star E is B, B star A is C, B star B is E, and then B star C would be A. This gives us the row for B, as B takes on its role with each element in V. So that would be B star X, where X can be any element in V4. Then we have P sub C, and that's just going to be C, B, A, E. So these are all of the permutations for these elements in V4. Problem number 3. On problem number 3, we have we've been asked to find two isomorphisms from Z to 2Z under addition, and recall that Z contains all of the integers. So here's the set of all integers, and 2Z is where we simply take 2 times each integer, and that would produce this set here. And we've been tasked to find two isomorphisms that would take you from Z to 2Z. And they would be phi of, let's call this phi sub 1 of x. And we'll let phi sub 1 of x be 2 times x, which means that for every x from Z that goes into the mapping, twice that value comes out. So 2x would be this set here, which is 2Z. But we could also take any value from the integers and multiply by -2, and the output would be, again, the set 2Z. And I decided to leave this in a different order, just for simplicity, because we know that in sets, order really does not matter. But if you were to take -2 and multiply -2 times the integers coming in from the left, you would see that 8, 6, 4, 2, and 0, and so on, those would appear first. And we know that these two are essentially the same, right? Because they contain the same elements. So these would be the two isomorphisms that would take you from Z to 2Z. Number 4. On problem number 4, we have been asked to define an isomorphism that from Z sub 2 to a subgroup of Z sub 4 under addition. And again, I've given the table here for Z sub 2 under addition. And I went ahead and decided to go ahead and include the table for Z sub 4. And again, this is just operating on that set. Going back and looking at the problem, we're looking for an isomorphism that will map you from Z sub 2 to a subgroup of Z sub 4. Well, a subgroup of Z sub 4 is the set containing the elements 0 and 2, because we have all of the group properties in this set. In other words, we have the identity value, which is 0. Of course, 2 plus 2 is 0 in Z4, so 2 functions at its own inverse. And of course, if you're working with integers, you're going to have the closure and the associative properties. So we're looking for a mapping that would take us from Z sub 2 to Z sub 4. Well, if we define it this way, and since we have so few elements, we can do it without too much rigor, all we really need to do is just define a mapping from each element in Z2 to a unique element in Z4. So I decided to go ahead and map 0 to 0 and map 1 from Z2, map that to 2 in Z4. So that would be an isomorphic mapping that would take all of the elements from Z2, and those elements are 0 and 1, and map those to a subgroup of Z4. Number 5. On problem number 5, we have the following. Suppose that group 1 and group 2 are groups and that E is the identity in group 2. Show that the function phi, which maps G1 to G2, defined by phi of little g is equal to E for all G in group 1, show that that has the operation preserving property. Let's go back and sort of digest what this is saying. Phi of G, in other words, phi is going to take any element in group 1 and it's simply going to send it into the identity element in group 2. And to show that this mapping has the operation preserving property, we have to show that phi of G1, G2 is equivalent to phi of G1, phi of G2. Well, if G1 and G2 are any arbitrary elements in G1, then we know that G1, G2, due to closure, has to be an element in G1. So that element would map to the identity. So phi of G1, G2 would be equal to E. And then we have to show that phi of G1, phi of G2 is also E. Well, phi will take G1 to E, and phi will also map G2 to E, and E times E would also be E. So we have found an isomorphism that, well, we have found a mapping that will map any element in group 1 to the identity in group 2. And we have shown that that has the operation preserving property. That's what we were tasked to show.